Welcome back. We're now ready for Newton's second law. And Newton's second law can simply be stated, and you've probably seen this before, as force is equal to mass times acceleration. This is probably, if not the most famous formula in all of time or all of physics. It's up there. It's probably up there with E equals mc squared. But that one's a little bit more complicated. So what does this tell us? This tells us that the net force upon an object is equal to the object's mass times its acceleration. So let's stay in the metric system, because most of what you'll do in physics class is in the metric system, and that tends to be because the metric system makes more sense. So let's say that I have a 1 kilogram object. Let's say I have a 1 kilogram object. So its mass is 1 kilogram. And it's being pulled down at, let's say its acceleration, so it's being accelerated downward at 9.8 meters per second squared. This should be familiar. This kind of units, these kind of units should be familiar with you from all the projectile motion problems. So the force applied on that object in order to get this type of acceleration would be, you just multiply mass times acceleration. The force would have had to be 9.8 kilogram times the meter, right? Kilogram times meter over second squared. That's the force applied on the object. And I say, you're saying, Sal, this is very messy. I don't like writing kilogram meters per second squared. And you are in luck, because there is a unit. And that unit is the Newton. 1 Newton is equal to 1 kilogram meter per second squared. So if I'm pulling down on an object at 9.8 newtons, that's just this, right? This is 1 newton. If I'm pulling down at 9.8 newtons on an object that is 1 kilogram, its acceleration is going to be 9.8 meters per second squared down. And notice I said the word down, but I didn't write it anywhere in the formula. And I guess we can imply that both force and acceleration have direction by writing this in the formula. That force is a vector and acceleration is a direct vector. And so we could have written 9.8 newtons, I don't know, this, you'll never see this convention, but we could say newtons down is equal to 1 kilogram times 9.8 meters per second down. So what can we do with this formula? Well, we can solve problems. So let's say that I have an object. So my object the mass of my object. And I'll differentiate between weight and mass in a second. Let's say the mass of some object is, I don't know, 50 kilograms. That's how much a normal person might weigh, or a light person. Mass weighs 50 kilograms. And let's say we're in an inertial frame of reference. We're in deep space, so we don't have all these other, the force of wind and the force of gravity acting on us, etc., etc. Let's say that I apply a force of let's say I apply it to the right. So we know that force is a vector. So let's say I apply a force of, I don't know, 100 newtons. And let's say I apply it to the right. So this is the object, 50 kilograms. And I'm applying a force to the right of 100 newtons. So what's going to happen to this object? Well, let's use a formula. Force is equal to mass times acceleration. The force is 100 newtons. 100 newtons is equal to the mass. The mass is 50 kilograms. 50 kilograms times the acceleration. So we can divide both sides by 50, and you get 100 newtons over 50 kilograms is equal to the acceleration. And it's 100 newtons to the right. I mean, I'll use this little arrow here. That's not a traditional convention, but that's why we know it's to the right. So it's 100 divided by 50. So it's 2. We get this weird units here. Newtons per kilogram, right, is equal to the acceleration to the right. this is also going to be to the right, because the direction of the force is going to be the same as the direction of the acceleration. So what is this? 2 newtons per kilogram? Well, if you remember, well, you could just guess the unit of acceleration is meters per second squared, but let's show that this simplifies to that. So we said earlier that, let me just switch colors, that a newton is kilogram meter per second squared. And we're taking this newton over this kilogram over kilogram, right? So that will cancel out with that, and you get meters per second squared. And you wouldn't have to do this on a test. You would essentially, if you did everything right, you would know that the unit of acceleration is meters per second squared. So you would have the acceleration. I'm just switching the two sides. Is equal to 2 meters per second squared, and it'll be to the right. To the right. So that's useful. We just figured out, based on how hard I push something, how fast it's going to accelerate while I push it. And you could use the same formula to figure out other things. Let's say I know that an object is accelerating. Let's say my acceleration is 3 meters per second squared to the right. Let's say to the left, just to switch things. And let's say that I know the force being applied on it. The force being applied on it is, I don't know, 30 newtons to left. And I want to figure out the mass. Well, you use the same thing. You'd say force, 30 newtons to the left, is equal to mass times acceleration, times 3 meters per second squared to the left. Divide both sides by the 3 meters per second, and you get 30 newtons over 3 meters per second squared is equal to the mass. 30 divided by 3 is 10. And then newtons divided, you can figure out that newtons is kilogram meters per second squared, so you're just left with 10 kilograms is equal to the mass. And it's very important that if you see a problem where the answer is given in I don't know, kilometers per second squared, or instead of giving it in kilograms, it's giving it in grams or decagrams, you should convert back to kilograms or meters, just so that you make sure you're using the right units. And that tends to be, frankly, I think the hardest thing for people. And we'll do all of that when we tackle harder problems. I think now is a good time to actually differentiate between mass and weight. And you've probably thought the two were interchangeable, but they're not. Mass is how much of an object there is. So, how many, you can almost view it as how much of the stuff there is, or you can almost view, how many atoms there are, but even atoms have mass. So just how much stuff there is. And another way to view mass is how much does the object resist change? And that actually falls out of F equals ma, right? Because if our mass is bigger, it's going to take a lot more force to make it accelerate a certain amount, right? If the mass is smaller, it'll take less force. So mass can be viewed as how much stuff there is of an object there is, or you can view it as how hard is it to change what that object is doing. If it's stationary, how hard is it to accelerate it? If it's moving, how hard is it to maybe stop it, which would essentially be decelerating, right? How hard is it to accelerate an object? Weight is actually what is the force of Earth upon an object. So your weight would actually change if you go from one planet to another, because the force of gravity changes. So your weight is 1/6 on the moon as it is on Earth, because the pull of gravity is 1/6. But your mass doesn't change. There's still the same amount of Sal on Earth as there is on the moon. So your weight, really, when you ask someone in Europe and they'd say, hey, I weigh 50 kilograms, you should say, no, you don't weigh 50 kilograms. You weigh whatever 50 times 9.8 is. That's like, 400 something. You weigh 490 newtons or something, right? This is mass. And it's interesting because in the English system, and all of us Americans, we use the English system, when we say that we weigh 10 pounds, we're actually using the correct terminology, because pounds are our unit of force. And so when we're saying, if I weigh, and I do weigh about 150 pounds, that means the Earth is pulling on me with 150 pounds of force. And it actually turns out that my mass is measured in a unit called the slug, which we might discuss later. Actually, we'll do some problems where we do it in the metric system and the English system. Anyway, I'll see you in the next presentation.